So in this lecture, we're going to be taking a look at the derivative and its relationship with extreme values. And then ultimately, we will finish by proving the mean value theorem, which is arguably one of the most useful and influential theorems, especially when it comes to differential calculus. A lot of the major results rely on the mean value theorem. And we'll have a chance to look at some of those later. So we're going to start with our definition of what it means to be a local extreme value. So we're familiar with the extreme value theorem, which gives us conditions that guarantee that f has an absolute maximum and an absolute minimum. So it means it's over the entire domain. When we talk about local extrema, it means we are restricting ourselves sort of to some local neighborhood around the location of that local max. And so let me go ahead and show you a picture of what I mean. So it's possible that your local extreme value is not a global extreme value. So I could have something like this, where I notice that at this location here, at this x0 value, I have a local extreme value, but it is not a global extreme value because I can identify, for example, this point over here, and that value of the function is higher. But I am able to sort of restrict myself to a neighborhood around x0. And in that neighborhood, I can claim that for any x value that I select in that delta neighborhood, its f of x value will have to be less than or equal to the value of the function at my local maximum. And so this here is my delta neighborhood that I'm finding. And so that's consistent with saying we have a local max at some x0, provided I can get this delta neighborhood such that any point in it will satisfy the relationship that f of x is less than or equal to f of x0. So that's just on the neighborhood. I can also define an analogous definition for being a local minimum. So for example, if I look at this place right here, here's a local minimum. It is not a global minimum, so I could call that, say, x1. It's not a global minimum because here's a value of the function that is smaller. But I can, again, put some neighborhood around it and guarantee that on that neighborhood, any x value that I select will have a function value that only gets bigger. So these are our local extrema. And we know from experience with calculus that when you have a max or a min of your function, you might expect the derivative of your function to be equal to 0 there. Now, there are some conditions for guaranteeing that. If you have a max or a min that occurs at an endpoint, it could just happen because you've cut off your graph and you don't necessarily have an extreme value there. So I'm thinking about something like this. Maybe I have something like y equals x squared. If I were to cut off my graph and only look over a certain domain, some a value here, then my maximum can occur at the endpoint, but certainly the derivative is not there, 0 there. I can take a look and notice that my tangent line has positive slope. So what conditions can we specify in order to guarantee that we have an extreme value? So this is, you might be familiar with it from advanced calculus. It's called the interior extremum theorem. It is not given a fancy name in Rudin, but I'm going to go ahead and give it its name here so we know what we're referring to when we cite it. So the interior extremum theorem, which we abbreviate IET. So this says, suppose that f maps the open interval AB to R. And suppose that this has a local max or min at some x naught that's inside this open interval. And that f is differentiable at this location x naught. Then this is enough to guarantee that the derivative is equal to 0 there. So it's important to notice here, this theorem is called the interior extremum theorem. It's the interior emphasis. X naught is occurring not at an endpoint, which means we don't have this graph over here. It has to happen at some interior point, and another thing that's important is that you need to know that you're differentiable at that location, because you want to avoid situations. You want to avoid situations where you have something like this, where you have an absolute max, or sorry, you have a local max, but the derivative does not exist at that location. So to get some intuition about how this proof is going to go, let's take a look at the case where we're working with a local maximum. An analogous argument would work if we took a look at a local minimum, but we will just show our proof will be without loss of generality, assuming that we're at a local max. Okay, so let me draw you a picture of something that looks like a local max. Oops, that is a local min. Let me draw you a picture of something that actually looks like a local max. So here is my local maximum. The moment I have a local max, I know that I can get this neighborhood around x naught where I can guarantee that my function values anywhere at over that neighborhood will all be less than or equal to the value of the function at my local maximum. So this is my n delta of x naught. The way that we are going to argue that the derivative is equal to 0 is by showing that it has to be less than or equal to 0 and it has to be greater than or equal to 0, and therefore the only way that can be true is if it is equal to 0 itself. And the way we'll do this is just straight up using our understanding, our geometric understanding of what a derivative is. We know, for example, if I grab points that are coming from this neighborhood that lie to the left of x naught, then when I go to generate a secant line for the sake of trying to converge toward the value of the slope of the tangent line, notice that any value that I pick will always end up with either, it could be possible that it has horizontal slope in the event that the local max value is achieved at two different locations, but assuming in the case like I've drawn here where f of x is strictly smaller, then you end up getting things that have positive looking secant slopes. And so just for the sake of including the case where it could possibly be 0, we have non-negative slopes from the left side. And if I do a similar analysis and I say, okay, well now instead let's work with points from the right hand side, and I look at those secant slopes, these now are going to have negative or potentially 0 slopes. So we've got non-positive slopes from the right. So this suggests, the graph suggests that we want to use sort of paths of approach. We know that when you have the limit of a difference quotient, if that limit exists, then it doesn't matter what path of approach you use. So we're going to use sort of sequences. We're going to take a sequence of inputs coming from the left-hand side of x naught and a sequence of inputs coming from the right-hand side. So the graph suggests using the sequential characterization of a limit. Specifically in the context of the definition of the derivative. So we're going to use some xn and yn, where they're each converging to x naught, but it'll be such that xn is coming from the left-hand side of x naught and yn is coming from the right-hand side. So each of these will converge to x naught, but we're going to exploit the fact that we know how f of x relates to f of x naught, and how when you choose left and right sequences, you also know how the sequence values relate to the value x naught. So let's get started on our proof. So we said without loss of generality, we are going to assume that f achieves a local max at x naught in AV. And we also are going to assume that f is differentiable at that location. By knowing we are differentiable, that means that we can use the limit along any path, and it will always give us the value of the derivative when we are generating our secant slopes. And so, and if, let's see, f is differentiable at x naught. Then we know that there exists this delta greater than 0. This is just the definition of a local max, such that for all x in the delta neighborhood around x naught, f of x is less than or equal to f of x naught. So what we're going to do is just assert the fact that because we're working on an interval and x naught is in an interval, x naught is a limit point of our domain. So that allows us to generate these sequences. So because x naught is in a b in the middle, x naught is a limit point. We know every value in an interval is a limit point. Of the set AB. So there exists x naught, xn and yn, and we're going to pull these from our delta neighborhood so that we know that we have the function, the relationship between function values, where we get xn less than x naught less than yn for all n, such that xn converges to x naught and yn converges to x naught. Something to point out, just so we have it later, is that when I look at f of xn, it has to be less than or equal to f of x naught, and f of yn also has to be less than or equal to f of x naught. that's simply because we are working with a local max value. So xn and yn are in this delta neighborhood. Okay. So because f is differentiable at x naught, we know that f prime of x, x naught, sorry, is the limit as n goes to infinity of f of xn minus f of x naught over xn minus x naught. Now normally the definition of the derivative does not use a sequence. It instead just looks at t values that approach x naught. But because I am differentiable, the path of approach doesn't matter, and so I can say that f prime of x naught will have to be equal to the limit of the secant slopes along my left-hand sequence. If I take a look at my top values, f of xn minus f of x naught, recall that we knew f of xn was less than or equal to that value f of x naught, and so this top portion has to be less than or equal to 0. But the bottom portion, since I am coming from the left-hand side, I know that the bottom portion is also negative. So that means that overall this expression that I'm computing the limit of has to be greater than or equal to 0. So I'm taking the limit of a sequence in which every term of that sequence, it's a quotient, but every term of that quotient sequence is greater than or equal to 0, and I know its limit exists. So that means that this limit value has to be greater than or equal to 0 by the order limit theorem. The order limit theorem says that when you have a sequence that's greater than or equal to 0 for all of its terms, and that sequence converges to some a, then its limit a has to be greater than or equal to 0 as well. Now that's true when you're working over R because you need to have order, but luckily for us our function is real valued and operates on the reals. So you can imagine that how the argument's going to go for the other side. If I were to think of the derivative at x naught, I could also characterize it as the limit as n goes to infinity along the yn sequence instead. And this time I'm going to have the same relationship on top because of the local maximum requirement, but on the bottom this time my y's are coming from the right hand side, and so this bottom term, it has to be strictly positive, which means overall I'm going to be less than or equal to 0, again by the OLT. So we have shown that on the one hand, 0 is less than or equal to f prime of x naught, and on the other hand, f prime of x naught is less than or equal to 0. It follows that f prime of x naught has to be 0. And we're done.